number 5 looks like it should be a u substitution problem because of the fraction. However, it's not the case. We have a single term, a monomial, in the denominator, which means that we can in essence divide both parts of the numerator by that x. So we have the integral from 1 to e of x squared over x minus 1 over x dx. Now, x squared over x, that simplifies to just x. So we have the integral from 1 to e of x minus, and then 1 over x. Does not simplify, but that's okay, because these are two expressions connected by subtraction, which we can easily antiderive. So we can go ahead and change the x to x squared over 2, and the 1 over x to the natural log of the absolute value of x, and that's being evaluated from 1 to e. When we plug in e, we get e squared over 2 minus the natural log of e. When we plug in 1, we get 1 squared over 2 minus the natural log of 1. The natural log of e is equal to 1. The natural log of 1 is equal to 0. So we end up having e squared over 2 minus 1 minus a half. So 1 and a half is 3 halves. So we have e squared over 2 minus 3 halves. Our answer is E. For number 6, we're told that f is continuous and f is the derivative of big F. So this is another way of saying that big F is the antiderivative of little f. All right. And we have to figure out what the integral from 1 to 3 of little f of 2x dx is equal to. All right. So we have an inner function here, so that means we're going to involve u. U is 2x, so du is 2 dx. We have the dx, but we don't have the 2, so we're going to modify that with a 2 on the inside and a 1/2 on the outside. So we have 1/2 the integral, and then we will have little f of u du. Right? Why? Because the 2 and the dx are equal to du, and 2x is equal to u. What we also need to change are the bounds, right? Because we're changing from x as our independent variable to u. So we're going to plug 1 and 3 over here in for x. Twice 1 is 2, twice 3 is 6. Now we actually have to perform the fundamental theorem of calculus, okay, which means we have to take the antiderivative of little f. Well, the antiderivative of little f is big F. So we got a 1/2, and then we have big F of u. This doesn't look good. I apologize for that. Evaluated from 2 to 6. All right. We're going to plug the 6 in first and the 2 second. So we have 1/2 big F of 6 minus 1/2 big F of 2. Our answer is E. With number 7, we have the integral from 0 to 1 of e to the negative 4x. So again, there's an inner function. The exponent is more than just x. So we're going to make u equal to negative 4x, and du is equal to negative 4 dx. We don't have the negative 4, so we need to put it in, which means we need a negative 1/4 on the outside. So we're looking at here negative 1/4 times the integral e to the u du. And when we change our bounds, we're going to plug 0 and 1 in here. When we plug in 0, we get 0. When we plug in 1, we get negative 4. Now some of you, your spidey sense is tingling. You know that these bounds are backwards, so we need the negative 4 down here and the 0 up there, which negates the entire integral. Well, the integral already had a coefficient of negative 1/4. Negative times a negative is a positive, so we have 1/4 the integral from negative 4 to 0 of e to the u du. Now it's time to take the antiderivative. So there's our 1/4. E antiderives to itself, and it's being evaluated from negative 4 to 0. So this is 1/4 of e to the 0 minus 1/4 of e to the negative 4. E to the 0 is 1, so we're looking at 1/4 minus 1/4 of e to the negative 4th, and that's D. With number 8, we have to figure out what k is equal to. Again, we're looking at u substitution. We have a fraction, or rational expression rather. So u is going to be equal to x squared plus 4 du 2x dx. We have the x, we don't have the 2, so 2 on the inside and 1/2 on the outside. So we now have 1/2 the integral from 0 to k. The 2x and the dx are replaced by du. X squared plus 4 is replaced by u. And oops, I screwed up. I should not have done the 0 and the k, because those are the wrong bounds. I have to plug the 0 and the k into here. So 0 squared plus 4, so this should actually be a 4. And then k squared plus 4 up there. Right. So, when we do our antiderivative, we have 1/2 du over u is the natural log of the absolute value of u. And that's being evaluated from 4 up to k squared plus 4. We're going to plug the k squared plus 4 in first. So we're going to have 1/2 the natural log. Since k is positive, and we're squaring it and adding 4, we don't need the absolute value anymore. So it's just the natural log of k squared plus 4. Minus 1/2 the natural log of 4. And we know that this expression right here is equal to 1/2 the natural log of 4. So now we have an equation. We're going to solve that for k. We see a half, a half, a half. We can basically, well, you know what? Let's change that up. Let's add half ln 4 to both sides. We know that 2 halves ln 4, that's just going to be a regular natural log of 4. So those wipe out. And move back over here. So we have 1/2 the natural log of k squared plus 4 is equal to the natural log of 4. And then we can get rid of the half. So that means that we have the natural log of k squared plus 4 is equal to twice the natural log of 4. All right, we have to do a little bit. We need our natural log here to go away, but this 2 is slightly screwing everything up. So we've got to use our natural log properties from pre-calculus. We know that if 2 is a coefficient, that's the same thing as making it the exponent of what we're taking the natural log of. We're taking the natural log of 4, so that's the same thing as the natural log of 4 squared, or the natural log of 16. All right, so what does that mean? Natural log of k squared plus 4 equals natural log of 16. The ln's match up, which means the k squared plus 4 and the 16 must match up. We subtract 4 from both sides. K squared is equal to 12, and therefore k is equal to the square root of 12. Our answer is D.